comment on one interesting aspect of this patient-specific approach, which is that, typically we have molecular pathways that are worked out, and they're in the papers and they're in the textbooks, and we think, okay, this is the regulatory architecture that regulates some aspect of health and disease. And then everyone understands that there are patient-specific genetics and epigenetics and those kinds of things that impact at the hardware level. These are all things that introduce novel components and novel properties into the function of that system. But there's another very important layer here, which I think has not been really mined like it should, and I think represents a massive opportunity for the future of basically, I think, of the same kind that happened in the information sciences when we went from the 1940s and 50s, when in order to program a computer, you had to interact with the hardware. Everything was about the hardware. And if you look at pictures, what that was, she'd be sitting there pulling wires, right, and rewiring the thing. And the reason you don't need to get out your soldering iron when you go from Photoshop to Microsoft Word on your laptop is that we've learned that when your hardware is good enough, it becomes reprogrammable, and you need to communicate with it, not micromanage it at a low level, but you need to communicate with it, and you need to manage its memories and so on. So as I'll mention momentarily, when we talk about our work, I think we are now beginning to understand that it's not only the software level, but literally on a kind of cognitive level, the numerous subcomponents of our bodies have memory forming abilities. They literally, quite literally, learn from experience. They have memories. Some of these memories are pathological. Some of these are beneficial. They are tractable to all of the tools of cognitive neuroscience, which is why I'm using the word memory. But these things have profound effects on how, both on the side effects and on the efficacy of interventions for individuals. So it's not just the hardware level and the genetics and things like that. It is also the memories that the various molecular pathways, cells, tissues, and so on in any given patient have formed. So I really applaud this patient-specific approach, because I think we've just begun to scratch the surface of it.
Wonderful. Michael, could you tell us a little bit about your lab's innovation, and especially around cancer and bioelectric signals?
Sure, and I'll share slides momentarily. I just want to give first just a quick introduction to this. So my perspective on this is that birth defects, failure to regenerate after injury, and we're talking massive regeneration like limbs and things that certain other animals can do, cancer and aging are really all fundamentally the same problem. They are a problem of understanding and controlling how groups of cells know what to build. Okay, if we had good control over what groups of cells could build, we could repair birth defects. We could cause the regeneration of organs, either in vivo or for transplantation. We could normalize cancer, and we could stop and reverse aging. Now, what is abundantly clear is that cells and tissues are able to navigate the space of anatomical possibilities. Right, you start life as a single cell. Eventually, you end up as whatever complex anatomy you have. And this is not a hardwired process. This is a process of active navigation of the space of anatomical possibilities. And we were all taught in our molecular and cell biology classes that, in fact, the question of how do they know what to build is a bad question. That you would standardly be told, none of these systems know anything. What you should do is apply open loop models of like cellular automata. There are local rules. Everything runs according to these rules, and then eventually there's emergence and complexity. Right? These are very popular terms, and eventually something pops out. What I would like to tell you is that for the exact same reasons that those kind of models don't cover all of cognitive science, right? We are well aware that animals with cognition have represented goals. They can deploy intelligent behavior towards those goals. They can navigate problem spaces and so on. For that exact same reason, it turns out that those kind of views, where the system doesn't know what it's doing and is simply rolling forward according to the rules of chemistry, those kind of models are insufficient for what we want to do here, for understanding biology, for understanding evolution, and for transformative regenerative medicine. Okay, they leave too much on the table. It turns out that the cells and the group, and especially groups of cells in your body, know what they're trying to do, in the same sense that a self-driving car has a memory of its goal, and it has the ability to do context-sensitive problem solving to meet that goal. They actually do have a represented end state that they're trying to reach, and they have degrees of intelligence to reach it. And so we, over the last 20 years, my group has developed novel technologies to actually be able to read those goal states. So we can actually look to see what are the memories that these cells are trying to implement, and we can see how they're encoded, and in some cases we can rewrite them for some transformative applications.